In this lesson, we're going to talk about inverse functions. Inverse functions can be denoted using this notation. So you'll notice that we have y equals f of negative 1 to the x. This is not an exponent of negative 1, but it is the notation that denotes an inverse. An inverse function basically reverses the process that we have it in a function. So for example, if you had x squared, squaring a number, then the inverse would be taking the square root. If you had plus 2 as part of your function, the inverse would be taking away or subtracting 2. When we're talking about looking for the inverse of a function, because we're looking for the opposite, what ends up happening is we actually inverse or switch our x and y values. So instead of xy, we now have yx. So in this first example, I have the function f as 4 points, 1, 2, 2, 4, 3, 6, and 4, 8. Those are 4 points that we could plot on a coordinate grid. In order to state the inverse of this function, all that I would need to do is reverse the x and y pairs. So instead of 1, 2, I have 2, 1. Instead of 2, 4, I have 4, 2. 6, 3, and 8, 4. So x and y have just been reversed. Now, if we want to find the equation for an inverse function, what we're going to do is still switch our x and y, but now we're going to have to do a little more work because we actually want to write this as an equation. So for example, if we have the function f of x equals 2x plus 1, and we want to find its inverse, the first thing I need to do is I need to write my equation in terms of x and y. As I said, we're going to be switching x and y, so I need to have both of them in the equation to start with. What I'm going to do is I'm going to replace f of x with y. By now you know that f of x and y are interchangeable. They're just two different ways of denoting the same thing. So in my function, I've let y equal f of x. I can then rewrite it as y equals 2x plus 1. In order to take the inverse, I'm going to switch x and y. So now I have x equals 2y plus 1. But we know that when we're writing an equation of a function, we need it in the form y equals something. So I need to isolate y and get y all by itself. So I've moved 2y to the left side, and I've moved x to the right side, and I then need to divide by negative 2. This is the equation of the inverse function. So I would write the inverse of f of x is negative x plus 1 over negative 2. And if you notice, in the original function, I was multiplying by 2 and adding 1. And here, in my inverse function, it makes sense that I'm actually dividing by 2, right? And if I actually simplify this a little bit, this would be x minus 1 over 2, right? Because this negative could be applied to both of these terms. So we see that I'm dividing by 2 and subtracting 1, the exact opposite operations as I had in the original function. Example 3 is very similar. So I have the function g of x equals x squared minus 1. If I want to find the inverse algebraically, I'm first going to let y equal g of x, so that I can write y equals x squared minus 1. I'm then going to switch x and y. So I'm switching x to the left side and y in here where x was. I then need to isolate y. So I'm going to move the 1 to the other side And then to get rid of squared, I need to take the square root. Now what you'll notice is that we have the graph here, g of x. This is x squared moved down 1. So this solid line is the graph of g of x. And on this grid, I've graphed the inverse, the root of x plus 1 with this dotted line. And what you'll notice is this is just the parabola turned sideways. But the inverse function here is not actually a function. So this inverse of g of x is not a function. Remember that in order for something to be a function, it needs to pass a vertical line test, meaning I need to be able to draw a vertical line through the graph and have it only intersect at one point. So this inverse is not actually a function. In order for this inverse to be a function, I would have to restrict the domain of the original function. So if I took x squared minus 1 and I restricted the domain to only include the right side of the graph, and then I took the inverse, you'll see I've drawn that here. So here is from 0 to infinity as the domain. And if I take that inverse, if I switch the x and y values, 0, negative 1 becomes negative 1, 0, etc., I just get this part of the graph, which is in fact a function. I could also restrict the domain to only include the left half of the graph, so this half. And when I take its inverse, what you'll see is that I also get a function. Because now it's like I've cut this in half, and now it would pass a vertical line test. In example 4, I'm asking you to verify whether f of x equals 2x minus 1 and g of x equals x plus 1 over 2 are inverses of each other. In order to verify if two equations are inverses of each other, all that you would need to do is use the same steps that we used in the above examples to find the inverse of one of them. So I chose to find the inverse of f of x. I let y equal f of x, so y equals 2x minus 1, and then I switched x and y, and then I isolated y by itself. So I moved the 1 to the other side, and I divided by 2. If you notice, when I do that, I end up with the function g of x. So this means that these functions are in fact inverses. If you notice, in this function, we're multiplying by 2 and subtracting 1, and in this function, we're adding 1 and dividing by 2. Since those are opposite operations, we know these functions are inverses. Now in this unit, the primary thing that we want to look at is graphing these inverse functions. So in order to graph these functions, we know that we're going to be switching the x and y coordinates. So the point xy is going to become the point yx. So in example 1, I've given you a graph, and I've asked you to find its inverse. All that you need to do is you need to determine, or you need to switch, the x and y coordinates. So you'll notice that on this table, I've listed points on the original relation. So the point -2, 0, the point -1, 1, 0, 2, 1, 3, and 2, 3. I chose those points as the main points on the line, and if I graph those or transform those points, I'll be able to draw the inverse of this relation. In order to do so, all I need to do is switch these x and y coordinates. So the point -2, 0 becomes the point 0, -2. And you'll see that I've done that for all of the points in this relation. Once I have all those points, I can graph them, and I get this green graph. Now what you'll notice is this is actually a reflection over the line y equals x. So this line y equals x is serving as an axis to reflect this relation over. If I look at the domain and range for both the relation and the inverse, you'll notice in the original graph the domain was negative infinity to positive infinity, or xer. And the range was negative infinity to 3, since this is a straight line. In my inverse relation, you'll notice that these just switch. The domain in the original was negative infinity to infinity, and now the range is negative infinity to infinity. And for the domain, it's negative infinity up to 3, which was the range of the original function. Now, I've also asked you to determine whether the relation and its inverse are functions. What you'll notice in this example is that the original is a function. This passes a vertical line test. Every x value only has one y value. But the inverse does not. It is not a function. If you notice right here on the graph, this x value of 3 has multiple y values. And when I draw a vertical line, I hit the graph on multiple places. So it is not a function. A side note is that if you have a function whose inverse is also a function, we call these one-to-one functions. Got one more example here for you, very similar to the last. In this example, we have this W-shaped graph, and I've asked you to find its inverse as well as the domain and range for each, and to determine if the relation is a function and if the inverse is a function. So you'll see I chose some key points on this graph. So -4, 3, -1, 0, 0, 2, 1, 0, and 4, 3. And I determined their inverse. So I flipped the x and y coordinates. I then drew those points, and you can see the resulting relation on the grid. When I determine the domain and range, the domain for the original relation is negative infinity to infinity, and the range is 0 to infinity. And when I look at the inverse, these just switch. So my range now becomes my domain, and my domain becomes my range, which makes sense since the x and y values are just changing. And if you notice here, the original relation was a function. It would pass a vertical line test, but the inverse is not a function. I could not draw a vertical line through this graph without hitting it in multiple spots. So that summarizes inverse functions. Try out the practice questions and let me know if you need any help.